So, welcome everyone. My name is Felipe, and I will be your host for today's webinar on how to use ScyllaDB for real-time, write-heavy workloads. Today's webinar is the first one, part of a series that we will be launching geared towards workload-specific characteristics. In a nutshell, basically what we will be doing is essentially to cover the content which we published in our database performance at scale book, which both Lubos and I here worked on together. During the webinar, Lubos and I will discuss common gotchas that may impact your database write performance, which key performance indicators you should be watching after, some optimizations you can apply, and of course, let's observe a workload running in action and discuss what is happening under the hood. All right? But before we get started, if this is your first time here and you are hearing about ScyllaDB for the first time, and given the poll questions, we have many newcomers here. Do know that ScyllaDB is the database behind game changers. ScyllaDB is used by organizations whose success depends upon delivering engaging experiences with impressive speed. ScyllaDB was built with a close-to-the-metal design that squeezes every possible ounce of performance out of modern infrastructure, which translates to predictable low latencies, even at high throughputs. And with such consistent innovation, the adoption of our database technology has grown to over 400 key players worldwide. So, guys, I'm quite certain that many of you will recognize some of the companies pictured here. And with regards to our write-heavy workloads, we could probably highlight Crypto.com for real-time trading, Ticketmaster, using ScyllaDB to support high traffic spikes during their ticket sales, and Fanatics, currently using ScyllaDB for supporting retailers worldwide for their e-commerce management. So ScyllaDB is basically used across many different industries and different types of use cases. So if you'd like to know more how we can help, feel free to book a one-on-one meeting along with me so we can discuss your use case privately. All right? So given that, quick word about ourselves. I am Felipe Mendes, and I am a technical director here at ScyllaDB. I have been here for 3 years now, and I started my career here at the company as a solution architect, helping and supporting many of our customers and our community of users, providing guidance on whether ScyllaDB makes sense for their needs. Along with me today, we have Lubos. Lubos, thank you so much for joining us today. And why don't you go ahead and introduce yourself?
Hey guys, so my name is Lubos Kosco, and I'm from Czech Republic. I basically work as a software engineer in ScyllaDB. I'm a ScyllaDB enthusiast, and I previously implemented an ad tech business in ScyllaDB as well. And besides that, I like to play on piano, and if I get some time, I like to go paragliding and get some flight.
Oh my God. Please don't kill yourself while paragliding, but otherwise enjoy.
It's safe, man. It's very, very safe.
Yeah, I never did it, so I can't say you are right. All right, so thanks, Lubos, and let's see basically what we have put together for us to discuss today. First, Lubos and I will quickly characterize what we mean when we refer to write-heavy workloads, right? So let's briefly discuss some of the challenges and also observe how they manifest in practice. Then Lubos and I will jump to the challenges and the trade-offs, where we'll discuss the multiple aspects driving your write throughput performance. Next, we will see basically ScyllaDB under load, and we have prepared a live environment, and there we will apply some techniques to see how performance either improves or degrades, all right? And then we'll discuss some best practices which we commonly see being misused in the field, followed by some success stories on how customers are using ScyllaDB to support similar write-heavy use cases. All right? So, Lubos, let's start with the characteristics of write-heavy workloads. And I think this is really important because, I mean, Of course, the overall idea when we talk about write heavy is that those workloads mostly write, right? So basically the ratio of writes is much higher compared to reads. But what really defines whether such a workload is real time really has to do with the high amount of latencies that your database is able to serve this high volume of writes in real time, right? We often say, for example, that if you have a workload somewhere close or beyond 50,000 operations per second, then ScyllaDB already starts to become a viable option for you. And this is not to say that other databases cannot get there. You can, of course, reach 50,000 or even more operations under a single Postgres machine, but doing so with low latencies will probably become quite challenging down the road, right? So I see that this slide basically discusses some of the challenges involved in scaling writes. And I'd like to your opinion on this. So for example, this first challenge here is basically scaling writes. And a notable example is DynamoDB, right? Because in DynamoDB, basically writes are 5 times more expensive than reads. So if you have a write-heavy workload, your workload will become much more expensive than if it were just a really heavy workload. What are some of your thoughts on that?
So you just asked the best question, actually, because you just asked about the money and the budget. And of course, like if the design of the database or the like principles how it works force you into going and buying lots of like operations or like buying something on demand which is very expensive, then of course your price per operation might get very high. And if you pay, for example, 7 times more with DynamoDB, then yeah, you probably need to start looking somewhere else and find something that has a better design where you don't have to spend that much money just for your rights. So that's definitely something that is important. I'm actually curious. You mentioned that write mostly, but you mentioned ratios. But what is this ratio like? So if I have a 50% writes and 50% reads, is this like write heavy?
This is a good question. That's actually a mixed kind of workload, right?
Okay, so we need bigger then. And
Yeah,
what's considered bigger then? Like
likely
60?
70-80% of
Okay.
writes compared to reads, right? But yeah, I mean, as I said, you can pretty much scale other databases, such as, for example, Postgres. But one of the problems of those databases is that they introduce locking, which can add delays and reduce the throughput. What are your thoughts on that?
So when I look at Scylla, for example, Scylla tries to be as locking free as possible. And besides LWTs, no other operations really lock. And of course, if you don't have any locking, then you can write as fast as your hardware can allow you to write. So the big difference between Postgres and Scylla would be that really with Scylla, if you design your data right and you don't need to use LWTs, there is no locking at all, which is quite nice. But then in the end, you come down to the hardware and you come down basically to your third point that you have on the slides, which is the IO bottlenecks. And you always have to keep in mind that in the end, there is some physics behind the operation and there is some disk that has to process the data, or there is some network that has to be able to ingest that amount of data. But usually what I've seen is actually that the disks and the IO on the disks are the most common bottlenecks. And CPU, of course, because sometimes you need CPU to process the data to get them written.
Yeah,
So
that's true. No, yeah, I think it makes sense. Let's not go through this list, exhaustive list, because otherwise we run out of time, right? But I think it all makes sense. I mean, there are definitely challenges in the internal database design decisions and your hardware, which drive your performance at the end of the day. There's nothing new here. So what we did here, following on, is basically we came up with this non-exhaustive list of use cases which are often very ingestion-oriented, but very different from each other. So Lubos, for example, I added IoT logging and monitoring, but you mentioned that you previously worked on EdTech and real-time bidding, and I'd like to hear your thoughts on that.
Yeah, so basically, this is a very interesting use case in the terms that you always want to be up to date with what your users are doing, because when you know what the users are doing, then you can properly target the advertisement to them when you do the bidding. And this means that ideally you want to have in a certain intervals, I don't know, once per hour, once per half an hour, having the data written sometimes in big batches. So those are like really heavy writes. And this data has to be ingested as soon as possible. So you need to get those writes to be done very quickly. You need to make sure that those writes don't interfere with reads. And you need to make sure basically that they get processed and they don't really impact the reads in terms of reconciling the data, like having the old data and the new data being merged together as soon as possible. So all these things basically are, if you think about them, hard, but then at the same time, if the database can do it, it's just great. So
Yeah, no, it makes total sense. And guys, if you are running some of those business, do let us know what's your use case in the chat, and so yeah, we can follow.
you know what's also interesting use case, like for example, time series, because there you basically write constantly, you have constant stream of writes, and also basically you don't read them that often. So that's also an interesting use case that actually
No,
leverages
definitely.
high amount of
Yeah.
writes.
And it's also a panda only, right? And no, it definitely makes sense. Logging and monitoring is actually very similar to IoT. It's also time series in a sense, but it's also different. I mean, if you're doing what Palo Alto Networks is doing with Scylla, for example, they're basically monitoring network traffic, right? We can easily imagine that some specific networks, specific device within a network will be busier than others, right? So you can create some sort of imbalance on your database. This is a good observation, actually. But yeah, I mean, I think that irrespective of the use case, we eventually needed to drill down to certain aspects that drive effectively your write performance. Because from the perspective of your database, not all operations are the same. And in fact, as we are going to see, some databases require less work than others in order to do heavy write processing, right? So Lubos, I would like to start with this because when if you Google ScyllaDB or quickly search, ask ChatGPT what ScyllaDB is, very likely you will end up with the definition that, hey, ScyllaDB is a write optimized database. And I went ahead and I started wondering, okay, but why? And it turns out that ScyllaDB follows this LSM tree approach in order to store your data. And by the way, this is the same approach used by other databases like Apache Cassandra, Apache HBase, and Google Bigtable. What really makes, what's the difference here between traditional database which use B plus tree and LSM trees?
Yeah, so if you think about it, like a lot of applications or databases and even like file systems, for example, if you think about ZFS is also using the LSM trees, and they are trying to optimize so-called copy on write approach, where basically the data, when it comes in, you just make sure that it gets written as soon as possible. You just append it to the disk. And if you look at the structures behind indexing, for example, then they have to support this as well. And LSM trees, you can see it on the picture very well, that you have like a data is being automatically sorted in the memory, usually based on the clustering key, and those tables or those structures actually can be merged very easily because you can just like append it together and you get like the sorted final data that is being flushed to the disks. But other databases, I think SQL databases use the B plus tree. They have a different approach. They actually don't optimize for the writes, but they optimize for the joins and for the relations, if you think about them. And they have B plus trees just because of the simplicity of reading the leaves. So you basically very quickly go from the root to the appropriate leaves that you need to read. But then if you look at the B tree as such, like you will see that if you have to do changes, it's not as easy as with the LSM tree, because you have to basically cut the whole part of the tree away, all the branches, and reshuffle them. And this operation is more costly than LSM tree. So this is the big difference. And you will end up basically with the conclusion that if you want to do joins or relations, okay, then you have to go to the SQL databases, because with the B plus tree, this operation will be faster. But if you want to basically
Yeah.
quick lookups based on the tokens or hashes or quick writes, then the LSM3 is a better approach.
No, that makes total sense. And
Yeah.
as a follow-up to that, I mean, how does the ScyllaDB write path works?
Yeah.
Okay, so it is a LSM3 database, but what happens when I write to the database?
Yeah, so I already mentioned basically that this is a copy on write. So there are some things that actually happen. Some of them are obvious. Of course, if your write comes into the node, the first thing that happens is gets written to the commit log. So this is a safety mechanism that if the node restarts for whatever reason or gets killed or you lose electricity, you will have a backup of the data that came in and you can replay it. Then it's basically processed into memtable, and the memtable, it will get prepared to be saved to an SS table. SS table is basically the format on the disk. And the important part is that this SS table, once it gets flushed from the memtable to the disk, it's immutable. So this is a very important thing to remember, because then when you write another data, it will not get appended to this SS table. You don't need to basically start merging it, blah, blah, blah. But you just basically get and flush a new SS table to the disk and you can go on. And this is like the optimized path, and the write path itself is not blocked by anything. So you see that there is no need for locking of all the SS tables or something like that. You just basically start writing.
No, yeah, it makes total sense. The only exception is the commit log, but there is no difference. Every database has it, right? It's a write
Most
ahead log.
databases have it. Yeah.
Yeah, and the rest is pretty much in memory until the main table fills up. Then we flush to disk. Then this process repeats over and over, and until we eventually get to compaction, which is something we are still going to be discussing.
We have a slide,
right?
or you have a slide on that now. So let's talk about this on the slide.
Yeah. But yeah, moving on. I mean, so this slide is actually very interesting, and I don't know if you recall, but basically a few years back, I was tasked with comparing ScyllaDB write performance across all three popular clouds, AWS, Azure, and GCP. And the thing is that probably those numbers, those performance numbers, they are outdated nowadays. This is a 3-year-old work, but the trend here is actually interesting, and it should still remain even in newer instances. So what happens here effectively, and I'd like to get your opinion on that, is that as we write smaller payloads, our throughput is, of course, higher. But if we look into the monitoring metrics here on the right-hand side, the CPU utilization basically becomes a bottleneck. And as we keep increasing the write size, we can see that CPU no longer starts being a bottleneck, but now we are requiring more works from the disks. What's going on here?
Like, look, in the end, with the writes, and a lot of people don't realize that, but if you write something that is small, it usually fits in all the buffers. Everything can be processed very quickly. It's being flushed very quickly. So everything is done like in the ideal way. You can basically get a high throughput of these small things, and they will be processed very easily. But then in the end, if you start putting bigger payload, like you need to allocate bigger buffers or multiples of the buffers in the system, like everything gets saturated, like network gets saturated, disk gets saturated. Funny enough, CPU doesn't get saturated, but the reason is very simple, because if you have CPU that is processing, I think you have like almost 200,000 queries. So if you have CPU processing 200,000 queries and CPU processing 100 queries, then there is not much work to do. And of course, the disk operations or the IO is offloaded to DMA anyways, so CPU doesn't have to really take care of the disk that much. So this is actually what's explained on your graph. So like the bigger payloads you get, the more resources you need to actually save those payloads, and then they become eventually a bottleneck, and you can only process a certain amount of them to be able to like get it done. But I actually noticed, yeah, you have I3s there. And you know what I would expect? I would expect that the I for I's would be actually on par or maybe even better than N2 MM16 on your picture. So your picture definitely needs an update, and I don't know how the LSV3 is doing, but the I for I definitely are better than N2 MM16. Yeah, but
No,
still you're right that basically it's very different situation if you have 1K payload and 4K payload and 32K payload. So that's obvious. So that's why I think streaming services are better suited for something bigger, and for smaller payloads, I think database is better suited than
Yeah,
streaming service.
makes total sense. Makes total sense. And yeah, I definitely need to arrange time to update this picture. But since we spoke about payload, I mean, what about compression? Because one particular concern is that if you have a write, mostly heavy workload, then chances are that you will have a concern of disk utilization, right? You are constantly blasting your database with writes, and I mean, disk doesn't grow on trees, right? So we cannot write forever and end up with height space amplification. So this slide basically are some pictures from our work Camille did a few years ago, where he analyzed the performance difference on selecting different compression algorithms in ScyllaDB.
You should definitely use compression. So, and it's funny that today's CPUs actually support compressing and uncompressing data very cheaply. And by default, I think you get in Scilla the LZ4 compression. And if you look at your pictures that you have there, actually this LZ4 is not that bad. It's actually quite nice. At the same time, if you look at Snappy, Snappy uses less CPUs. So if your workload basically needs more CPU, you can probably save some cycles with Snappy. It's not that much, but you were talking about storage and about storage usage. So you can actually sacrifice some of the CPU for the saving the disk space. And based on your tables, they're actually hard to read. It's small, but I can probably read some of them.
Yeah.
I think the ZSTD1, when I compare it, it gives you like 10, 15% better. Yeah, you can point it. You sacrifice a little bit of CPU, and in the end you get 10, 15% disk savings, which is nice. Like it's better than nothing. But you can still decide between those three. I probably wouldn't go for the biggest one, for the ZSTD9, because you should still keep some CPU or some spare CPU for other tasks. So, but the ZSTD1 or LZ4 or Snappy look like good choices.
Makes total sense. Yeah, deflate is also interesting, right? Because deflate, I think it's the one which saved the most. And I mean, it's flush time is slightly worse than LZ4 and Snappy, but if you want to save more on storage space, deflate won, at least for this particular set of workload coming
but
benchmark.
The question if it's worth it, like if you look at it.
Yeah.
So
yeah, no, it totally makes sense. So I think the main takeaway the audience should get is basically you should pick your battles wisely, right?
Yeah, you can even pick based on your data model, for example. I know that there are data structures, or I don't know, some aggregations, or if you are using aggregations, you want to save the CPU rather for them and rather sacrifice the disk space. So I still have a feeling that the disk space or storage is cheaper than CPUs. So you have to choose wisely.
Yeah, maybe we need to benchmark that in the future as well. But I mean, continuing on compression. So one thing that I recently learned is that ScyllaDB, not just ScyllaDB, but also other databases as well, they have this parameter which is called compression chunk size. And I think most people don't realize that. But compression chunk size basically means that when compression is working along with your data, compression will basically split your data into smaller blocks or chunks. That's why it's called chunk size. And then each block will be compressed separately. And we do have a blog where we analyze the performance impacts of comparing different chunk sizes. But I would like to hear from you. What are the main trade-offs users should know when and if they want to tune this setting?
Yeah. So of course, basically, you have to realize where do you want to optimize. If you want to optimize the reads, then smaller chunk size will actually get you better handling of the reads, and the bandwidth to read the data will be reduced, and you will get like smaller latencies for reads. But we are talking about write heavy workload, and write heavy workload ideally wants all the bandwidth that it can get. And in this case, I think you are better off with the larger chunk size, because the bigger the chunk, like the more data you can deduplicate basically and compress in a sense, and you get like better disk usage. And of course, the write will be, you can fit more of these writes in the same bandwidth
Yeah,
and
you
write more
can get
data
more
in parallel. Yeah.
sequential write performance, right? Yeah,
Yes,
makes total
yes, you can
sense.
get more done. So
Mm-hmm.
at the same time, like I am actually happy that you have on the slides the other Scilla block sizes. So basically people can go and look at other sizes that we have in the Scilla and probably can align to them. I know that Scilla actually can detect even 4K disks, and it will align its sector sizes
Mm-hmm.
to a 4K disk, which is quite cool. So if
Mm-hmm.
you want to really have a fast write heavy workload and you get 4K disks, then you can be happy. Scilla will just use it out of the box and you can just enjoy.
No, yeah, definitely. And yeah, this is not a setting which is typically changed from the defaults, but yeah, it's definitely another way for you to further optimize either your reads. But remember, guys, um, you will always lose something in return, right? As you optimize for one thing, you may lose on
Yeah.
another. And I think, Lubos, the next slide is actually quite interesting because since we are talking about trade-offs, we eventually will have to discuss about compaction, which we briefly saw when we were talking about the ScyllaDB write path. And what is it really?
We already touched the topic. So if you remember a
Mm-hmm.
few slides back, I said a very important sentence, which basically is that SS table is immutable. So if you get it written, the only way how to basically get the data rewritten again is to compact it. And that means usually that one or more SS tables get together and they get completely rewritten, and new SS table is born and all SS tables are basically freed up. And this compaction strategy is like there are a few of them. I think there is ICS, STCS, LCS, and time window compaction strategy. They all come with different traits, and they all are targeted against different use case. So I think by default in the enterprise Scilla, you get the ICS, which is like a hybrid compaction between size tiered and LCS. But the goal is basically that size tiered and ICS, for example, they are trying to avoid the write amplification, and you don't want to basically, if you are write heavy, you don't want your SS tables to being rewritten like all the time. So for example, for a write heavy workload, it's an anti-pattern to use the leveled compaction. So leveled compaction is actually exactly for the opposite use case where you have lots of reads and only tiny amount of writes, because with the writes, the leveled can do the amplification on the writes almost 40 times. So each byte or each data that gets written, it can be rewritten so many times that you really don't want to do that. So of course there is, for example, this time window compaction strategy, and the time window compaction strategy will be optimized on the time series data. So if it gets written like in a sequential manner, you get it broken up by windows, and then it will optimally basically handle the windows, TTL them away, and so on and so on. And again, it's trying to remove the write amplification.
So effectively, if I have a write heavy workload, then I mean, eventually I need to pick my own compaction strategy. I should avoid the level of compaction by all means. And yeah, basically this eventually drills down to what is the amplification I want to avoid, right? I will have some amplification, but it depends on what is the trade-off I want, right?
We actually explained the amplifications, and I think there is a maybe we can share the link about how to pick the compaction strategy so people can choose based on their use case. But of course, for the write heavy, you would want to go with the size tiered or with the ICS ideally in enterprise. And if you have time series data, then time window is a good choice.
Okay, perfect. No, yeah, that totally makes sense. And now, I mean, we spoke about lots of things, and I wish we had infinite time to discuss more thoroughly. But as we promised you, what I did basically, I spun up a cluster, and I've let some workload run. By the way, it's just small. I can definitely zoom that in. Let me know if it's better for you.
It's better,
And
at least I can see it better.
yeah, thanks. And what this workload is basically doing, it's basically a write heavy workload, right? So you can see here that we are sending 90, 60K, close to 100K requests per second against the cluster. And most of those requests are actually writes. And how do we know? Because here on the replica side, we can see that those writes are basically being amplified because we need to replicate data, right? Since ScyllaDB is a distributed database, etc., and so forth. And we have a much smaller level of reads. So this is definitely a write mostly use case.
What's your replication
and
factor?
It's 3. Yeah, we are
It's
replicating 3 times. Yeah. But what I'm seeing here, Lubos, basically is I'm happy with the latency. So if I scroll down here, I'm like, oh, that's nice. I mean, I am pushing the cluster
to the
really
limits.
hard. And I don't think it's yet at the limits, but we are pushing the cluster a lot. And this is just a 3-node cluster. I forgot to mention about the size. This is for a 2x large, so only 8 CPUs per node. Nothing, oh, that's a super machine. It's a small cluster. And my latencies are actually great. I'm happy with it. But one thing I don't understand really is sometimes I have those spikes here. Yeah, I don't know if you can see it then clearly. Maybe I should just zoom in, but
I can see them, and something is happening. So something, because I think if you are doing a constant write of 100K, I would doubt that this is client, and I would expect it's something else. Maybe, I don't know. Let's have a look at the bottom and at the detailed latencies there. Maybe at the payloads, maybe at the compactions. But do you use any special things, or it's just a plain table?
So this is basically a default table. The performance you would get from just creating a regular table on Scylla. The payload question you made is actually interesting. So I'm scrolling down here while I'm talking. That's why it's taking a bit too long. But you can see here average received payload size. A bit more than 1K. So 1 kilobyte payload size. And here you can see those spikes. Those are actually reads.
When did you start it? You started this before the call? Because I'm wondering if the compactions started to kick in already.
That's a good question. So this workload is running for quite some time. So as you guys can see, it's almost 2 hours now. So it's not something that, hey, we are running for 5 minutes and done, boom. It's actually been running for some time. So it's stable, but I don't understand those latency. Small spikes, but they're still spiky. And with regards to compactions, I guess that's what I should be looking at, is it?
Yeah, so you basically see that it's exactly as I told you. So the SS tables eventually need to be matched together. Like if you overwrite something, if you overwrite a partition key, or I don't know, if you delete something, then you eventually want this data to meet together, so it will be deleted from the disk. And I would expect that all the spikes that you see there are the compactions. And I think Scylla is actually doing a very good job, because if you look at your latencies, average and P95 is almost straight line, and you only see a small impact on P99. And even this impact on P99 is very tiny. So I think the compaction scheduler and basically backgrounding the compactions is actually doing a great job, because the impact is really small. Like it's in terms of microseconds, no, like 10 microseconds or something like that. So this is quite nice. I can see that you have, or you're using only 50 compaction shares. So that also I think is the impact. If you look at the right side, this one. Yeah, so I think queries have 1,000 shares by default, and this is only 50. So I think the scheduler is doing a great job here. So, or if you set it to 50, then it's you that are doing the great job. But I think this is scheduler. I don't think that you changed anything here. Did you? No.
No, it's default Scylla, default Scylla settings.
So Scylla is keeping this as a background operation because it knows the queries have the priority.
Makes total sense. Yeah. So let me ask you this: what can we do here in order to add some variance? I mean, SilaDB is being super fast, and I like what I see. How do I add some noise?
So how about we do some write amplification? How about we increase the number of writes with, I don't know, materialized views? How about that? Would that work for you?
Okay, that's a good idea. So create a materialized view.
Yeah, let's try it.
Let's try that. So I have my terminal here, and this is the workload running.
This looks like Cassandra
so
stress.
it's kind of Cassandra stress, but it's not. It's actually our Rust-based CQL stress, so it's in Rust. So
okay.
We decided to rewrite Cassandra stress just because, you know, we can say, hey, we wrote it in Rust.
I would expect
but yeah,
Rust would be faster a bit.
Yeah, but let's definitely create a materialized view. I think I have a statement here, so I can simply copy and paste. Yeah, I do. So I will create it, and let's see. Oh, I have a syntax error. I think it's the primary key. Yeah, primary key. Sorry. P0 and key. And I think that's it. Yeah. And okay, so we should have created a materialized view by now. And then I guess we should now get back to the monitoring. Or should we see the loader? Let's see the loader.
Let's see the loader. I'm curious because I think it started.
Yeah.
So there was an impact on performance. This is the average latency.
Yes. Yeah, I can see the latency increasing. And let's see our throughput. I mean, are we getting the same throughput as before? Oh, okay, it's going down. So what is going on here?
So you basically increased the number of writes because now your write has to go to the base table, and at the same time, the materialized view that is built on top of the base table has to be upgraded or updated. I don't know if you are still building the materialized view. I think you still are. So
it's
I don't
running,
know how.
yeah. So
I don't know
the
how long
database
will it
doing
take.
something.
Yeah, but you see that you're already getting back throttled. So the Scilla is already pushing you back, and the stress tool or the tester tool that you are using is going down. And it's interesting, if you look, everything is going down, but the writes per instance on replica are going up.
Yeah, that's a good observation. I mean, interesting. So yeah, even though we are basically throttling the client because we are actually writing more because of the view. Is that it?
That looks like that. So I would expect basically that your single write that was before with the replication factor 3, it was actually 3 writes in the end. I would expect that now it's basically 6 writes. So a single write would have to be translated into 6 writes on the replica. So you basically doubled, or at least doubled, your number of writes.
Yeah, let's see if that's the case. I mean, I'm doing 43K, and yeah, you're right. So
261.
Beyond 200 something, yeah, which is 6 times, yeah. Nice.
Yeah, so don't forget that from your coordinated requests, there are 10K reads. So you have to get rid of 10K, and only the rest is so 41 minus 10 is 30, and then 30 is multiplied by 6, I would expect. For the MVs.
No, just totally makes sense. And there's another thing that's happening, right? So the materialized view is building because it's always needs to be paired with the view replica. No, but I think this is enough. I mean, quick demonstration, really good. I think the next section we have in our slides are basically for us to discuss why this happened, right? So let's focus on here. Let's talk about some patterns that can be very detrimental to performance. And we often see in the field, right? So, Lubos, the first one we've got was batching. And I kind of get why lots of people stumble upon this, because in most people come from the relational world, right? Where, okay, if I have to write in just tons of data, or just batch everything and send against the database.
You want to save network traffic.
Exactly. Why is it an anti-pattern, and how to mitigate it with ScyllaDB?
Yeah, so in SilaDB, actually, I would like to first say something else. So I see that at the bottom of your slide, there is unlocked batches. This is actually quite important because a lot of people coming from the relational databases, they think that they have to use locked batches, but locked and unlocked, this is just a fancy server-side retry. So I think it's an anti-pattern to use locked batches. So if you can avoid them, avoid them. And the unlocked batches, they should actually be prepared in a way where the coordinator processes only the data that belongs to him. Like every single of these small Scyllas that you have there, it has its fair share of the data, and that's the data that it should be taken care of. Like you don't want the coordinator to be delayed with the data that doesn't belong to it. And this is very easily done because the client can detect which data belongs where, and it can even basically create the batches and group the batches by the primary key. And this is the important part here, that you want to be
So
grouping.
basically, do this,
Yeah.
right? So if I'm writing to several different keys.
This is an option. Yes, this is an option. You can prefer the individual insert. Like you can break down the batch into smaller inserts, but that will actually beat the saving on the networking. But you can also go and you can also like just batch by primary key. So
so like this.
Oh, you have a picture.
If
Okay, great.
yeah,
So yeah,
if it's
yeah.
to the same partition, right?
Yeah, you mentioned that you have a replication factor 3. So this picture is actually very nice because this means, okay, I am the coordinator for this data and there are 2 more copies. So I just basically update myself and 2 other copies, and I don't have to wait for anyone else, and this batch will be done. And batching by the primary key is actually the good thing. There is actually, you can go even beyond that because the client knows the token ranges that belong to a single node. And you can even batch, I think, by all the tokens that belong to a single node if you want to go even higher than that. But the crucial is basically send the data to the coordinator that is at the same time the replica to avoid all the extra network hops for writes.
Okay. So yeah, good recommendation about batches. And going back to our demo, maybe we should have here order the slides, but anyway, views and global indexes. So as we have seen, we created a materialized view. Our throughput automatically went down. Why that happened? I mean, what's happening really?
Yeah, but this is exactly what you used. You used the global index. You didn't use the local one. I think you had to create materialized view. Yeah, so you used exactly this. So what's going on is basically if you're updating the view, you basically get a single operation. In this case, for the global indexes, a single write will be actually translated into 2 writes. So there will be a delete and an insert. So you end up, instead of 1 operation, with 3 operations. So, and this is basically just to make sure that the view is consistent. That's why basically we are issuing the delete and then the insert. So
okay, and makes sense. And as we saw in the metrics, I mean, we saw the 6x more, right? Yeah. And
this was amplified or multiplied by the replication factor. So of course,
yeah. And Lubos, we do have another kind of indexes, which are local indexes, and also features like change data capture, CDC. What is the difference between a regular materialized view slash global indexes with using CDC and local indexes? There's definitely still a write amplification here, right? But it's different.
There is, but it's much smaller because local indexes, they are actually by definition smaller because in the local index, you are just changing the partition key and you just basically reorder the data with different partition key. And because of that, it's okay just to do the inserts or actually upserts to the index, and you don't have to do 2 operations. You don't have to do delete and insert, but you just do insert. Your picture is actually confusing because you have insert into index and insert into CDC, but it's just, I think you want to just explain it's different technologies or different features used. So the first one is the local index, second one is the CDC, and you can pick like whatever you use, it will be just one. So here basically amplification, the write amplification is basically just 1 write on top of your current write. So write amplification is 2, while with the global index it was 3.
Okay,
so
yeah.
like this needs like you choose a feature and you use the feature and you need the resources. So you have to basically account for the resources and keep this in mind. Like you don't get the feature for free. There is always something.
Yeah,
some
no,
price.
and I think it just totally makes sense because I mean, even though you may be writing heavily to against your database, at the end of the day, you have to read your data, right? So sometimes you may need to create an index or a view, and as we have seen, I mean, this will amplify your rates a lot. So always take that into consideration when you are using it. success stories, right? So lots of information here, and now let's get to the last part of this talk, where we'll discuss how ScyllaDB is being used in production to support a variety of use cases. So the first one Lubos and I brought to you was Zillow for real-time property updates. And Lubos, I don't know if you remember the story, do you?
I vaguely remember it, and probably you were looking for a house to buy, no?
Yeah. So basically, Zillow had this problem where they needed to consume records from different producers, and that introduced lots of out-of-order rights. And the problem with receiving out-of-order rights is that they could lose updates if they weren't going to naively ingest data to the database. And one of the things that Zillow eventually realized was that they could not use SQL for that, because given that, as we spoke, SQL basically does row locking, that would introduce contention and ended up undermining their latencies. So what Zillow did was basically they used this particular feature using timestamp in order to manipulate the rights, the time of the rights, so that every record would get ordered and they would effectively overcome their scaling problems. And what happens basically, go ahead.
Yeah, they essentially used the fact that with ScyllaDB, the last write timestamp wins. And this way, basically, they always were sure that whatever they wrote later would get merged with the stuff before, and they wouldn't get overwrites. So
yeah,
this is
and
nice trick.
they wrote a blog post about it. They even have a talk. And Zillow does use ScyllaDB for write-intensive traffic because they need to update frequently their property listings on its platform, need to notify customers, etc., and so forth. And the next customer I brought was basically Traction. Traction is actually an IoT use case. Lubos, I worked with them when they started engaging with us. And what they did is they realized they were facing Mongo scaling problems. And they said, okay, let's start evaluating other databases. And they decided to evaluate Postgres, Mongo, and ScyllaDB. And they decided to eventually go with Scylla. So what I like about this slide in particular is that on the right-hand side, we can see that ScyllaDB is doing 10 times more traffic than Mongo. But this is not all. I mean, if we look at their latencies, we can see that even at higher throughputs, ScyllaDB, while MongoDB latencies were like 700 milliseconds-ish, ScyllaDB latencies went down to 40 nodes on similar infrastructure. So as you can see, that's the reason.
High throughput, and lots of writes. Actually, yeah, Scylla will shine there just because it divides and it can optimally save the data.
Yeah.
So it doesn't surprise me at all.
Go ahead. Yeah, and the last customer I brought today is Fanatics. We spoke about Fanatics at the beginning, and Fanatics is an example of a retail company using ScyllaDB at scale. So Fanatics' story is this: they were struggling with Cassandra in order to support their e-commerce and business partners, and in particular in Cassandra, they had a very large cluster deployment, and even then they would observe, timeouts, queues, the request getting queued and throttled during their data ingestion process. So with ScyllaDB, what happened is basically with a 3-node cluster, just like I showed you, a 3-node cluster was enough to resolve all their problems and bring them back to stability. Any comments here?
So you can sell them your cluster that you showed us before, because it was also doing like a solid, I think it just 100,000 now. Yeah, okay, so maybe
something like that.
Use more CPUs than 8 per node.
Yeah. Yeah.
Yeah, but this is definitely write heavy. This is definitely write heavy, because if they're writing the orders and shopping carts and products at the same time, then yeah, you want to make sure that this is rock solid and just flies.
And the overall idea of retail is that consumers should never stop buying, right? So
It's a constant
all right,
rise.
yeah, let's move on. Last poll for today, guys. Please let us know how much data you are currently managing under your database. This one is particularly interesting, as if you're here, very likely you are right mostly, and often those workloads are very storage bound. All right, so thanks for your answers, and just basically brings us to the end of today's presentation. So before we start the Q&A, we've left here some resources for you to continue learning more about ScyllaDB and how to optimize performance. If you haven't done so already, visit our blogs at ScyllaDB.com to learn more about our technology and cutting-edge new features. If you care about performance, then please register to P99Conf, which is happening late in October this year, and we'll count with speakers from industry-leading experts and companies such as Red Hat, Netflix, Uber, Tiger Beetle, and of course, ScyllaDB, among many others. All right? And lastly, in 2 weeks from now, we will live stream our DynamoDB cost optimization masterclass. And there we will have presentation from DynamoDB expert Alex Debris, SADA CTO, Miles Ward, and myself from Scylla. All right? And you guys can find the link to all of those resources and upcoming events by following the link in the chat. So, Lubos, we still have some time left. I still haven't checked our questions, but I see we definitely have some questions. So is there any particular one you would like to tackle, or should I basically pick a random one?
Yeah, you can pick a random one if you want. I think they are all interesting, and they all actually have very good answers. So let's...
So an anonymous attendee is asking, can I book a meeting with Lubos? I'm from Czech Republic too, so it might be easier to discuss with him in native language. So Lubos, we received this question as by an anonymous attendee. Why don't you write your email on the chat window? So this anonymous attendee can know who you are. In the meantime, there is another question which is asking, when we refer to write-heavy systems, do we only mean eventually consistency system requirements? What about this, Lubos? What are your thoughts? Because definitely can be write-heavy workloads which are not necessarily, cannot necessarily be eventually consistent, right?
So I think what you were doing in your test, you were already doing full consistency, no? Or actually, you were writing with quorum or with one, the test? Do you know from the
Quorum,
quorum? Yeah, with quorum. So basically, if you think about it, Felipe was already showing you a demo that was presenting the full consistency, because if you write with quorum and if you read with quorum, then your queries will be always consistent. So you can lose a full replica and you still will have the database up and it will still work with full consistency. So yes,
Great.
write heavy, and Scylla is by default trying to keep fully consistent. So at the same time, like there is a gap theorem about it, so we can talk probably for a long time about it. But if you don't want to jeopardize your HA and you want to be sure to perform maintenance, then I guess this quorum for reads and for writes is the best approach, because it gives you a chance to have your Scylla HA and maintainable, and at the same time keep full consistency.
We have one question. You showed some comparisons of MongoDB versus Scylla. Do you have similar comparisons of AWS DynamoDB versus Scylla that you can share? So we do. I don't have the link right now, but if you go to our website, if I recall correctly, ScyllaDB.com/compare, you can get our comparisons with DynamoDB. We also have several talks about customers who transitioned from DynamoDB to Scylla, exactly to reduce some costs. And as I said, is on the slide here on the screen, we are also going to have a masterclass covering exactly this, how to optimize DynamoDB costs, and or look into alternatives. So of course, looking into alternatives is definitely going to be one aspect being covered in that.
There is a question basically whether it's just write heavy and write optimized, or if it's read optimized as well. And I think it's a good question because you basically like forecasted Felipe's next meeting, and I think your next meeting will be about read heavy use case, correct? Yeah, I'm not sure if Felipe can hear me, but the next session basically will be about read heavy workloads, and you can definitely optimize read heavy workload as well. So this definitely works too. I'm not sure what are other questions there.
I think I dropped it briefly, no? Haven't I?
Hey Felipe, yes, I think we lost you. I was talking to you and
Yeah.
suddenly there was no one. I was just saying
Sorry.
basically that people were asking about your next session regarding read heavy use cases, and they want to see whether Scylla supports also read heavy use case as compared to write heavy.
This is
So
definitely going to be in our next upcoming webinar on really heavy workloads. So stay tuned for our upcoming events. And ScyllaDB has its own cache. And we also have run a comparison of ScyllaDB versus a cache. So like Redis, main cache D, and such. And we have interesting performance numbers to show there. But yeah, no, definitely ScyllaDB can also be used as a good fit for really heavy workloads. Thanks for addressing this question. And Lubos, we definitely do have tons of other questions, and we are going to follow on because we are running short of time, which each one of you separately via email. Did you wrote down your ScyllaDB email to the person who asked it? Yes, no?
Yes, I can ping my email there as well.
Yeah. And in the meantime, guys, basically, stay tuned for more of ScyllaDB. Here are our social media links. If you have ScyllaDB specific questions, don't hesitate to ask in our forum or in our Slack, and then me and Lubos can jump in and help you accordingly. All right? So we are on top of the hour. Lubos, thank you so much for being here today.
Thank you, Felipe.
See you guys next time. Bye.
Cheers, guys. Bye.